Oops.
The
Well,
protons and the electrons equal the mass.
the protons and the neutrons.
Oh, great.
I know. Neutrons have the job of being heavy, and electrons have the job of being charged. Protons manage to do both. So
I'm gonna use it in this
it's kind of interesting because, like, if one of the things that Rutherford found was he wanted to know how big are these things, right? You have to just figure out not only like, hey, what's in the middle, but like what's the relative size. And so he worked out that there was like this little nucleus, and the what's that?
I can't see what you're like. Are you
Oops.
drawing anything?
I am drawing something. Is it not showing up?
I can't. No, I can't see. I mean, I don't know if anybody else can see, but I can't see.
That's weird.
All I see is a little red dot. Oh, a red dot and now a red circle.
Yeah,
All I
that's
see, all I see is black.
no.
Oh,
Oh,
is it?
are you pinned to? Does it have my name on or my letter on there? Or
Yeah. So,
uh,
Dr. Norman did, or it says Deborah Norman is person.
try to pin it to just click on the
Is it the pin button?
yeah, put your pin on the presentation.
This one.
What's going on, man? This is we're having all kinds of weird issues. I need to.
I could take over as a main
I
presenter, but
No, don't do that. That's someone mentioned last time that if you go to the bottom of your screen and you click on the, I guess you have to click on the U on the bottom left, and then it,
Those three little dots.
and then
oh yeah.
yeah, and then you'll have the three dots available to you,
Yep.
and then that can change your settings so that you can um, probably what would that be? Change layout. Is it change layout or is it just settings? Do you go to
It doesn't in settings. It doesn't really have anything.
nope? But yeah, the change layout should probably do something. So
This is frustrating. Let's try that. Nope, still nothing.
oh dear.
Just fine.
Well, that's very frustrating. Ugh.
Well, let me go out and then come back in and see if it works.
Okay. Um. Okay.
It's weird. How come I can see it and she can't?
Yeah, I know. It's
Did.
always a conflict of settings and stuff that's
I'm
difficult to.
back. I can see it.
Oh, okay. I just you never know. There's so many stuff going on with settings. Well, okay. So good. Okay, so one of the things Rutherford was looking at for just a regular old hydrogen atom here is the electrons zooming around this circle, kind of like a planet, and then the nucleus here contains within it just the proton, right? And then even if you put like something like a helium atom where you had like two protons and then two neutrons, right, in there, then still the size to be quite small. So the radius here is about 10,000 times larger than the size of the nucleus itself. So if you wanted to look at that in terms of the volume of the atom, then you'd be dealing with, because the volume of the atom is cubed, right? It's a distance cubed. Volume is always length times width times height type dimensions instead of just length, right? So that means that if you go into your calculator and you multiply 10,000 times 10,000 times 10,000, that is how much bigger the lowest n equals 1 energy level is, the nucleus of the atom. So let's do that real quick. I get my calculator out, and we'll do 10,000, and I'm just gonna cube it because it's the same thing, right? That's a lot. 1,000 billion, right? The volume of space that the atom takes up is 1,000 billion times bigger than the space that the nucleus takes up. So the answer to is the glass full or half empty is that the glass is 1,000 billionth full. The rest of it, all that water that you see in the glass, is really mostly just empty space. It's wild, isn't it? So if you take another of these though, and another atom, we put them like side by side here. Oops. Like this. We put them side by side like this, right? And we kind of talk about them like they're balls that are kind of squished together on here, but in fact, it's a little bit different than that. But this is the Bohr model, so we're saying, yeah, most of the weight is right here, right? So for the helium atom, then that's 4 mass units of mass, right? And then the electrons out here weigh hardly anything at all, but they take up a whole lot of space. Let's see if I can get it to work. My goodness. N equals 1. So this is the N equals 1 shell. Okay? A subshell. Or shell. Now when I look at L here, I'm able to check whether it's a S, a P, a D, or an F. So S is the most basic. I can't go anywhere else. I don't have any other options. Why? Does anybody know why? Why I don't have a P or a D or an F as an option here?
Isn't it because it's at the bottom layer, the bottom of the building, first shelf?
That's correct. Yeah, because N equals 1. And you got no options at N equals 1. You can only have the most basic type of shelf. When we go up in level to N equals 2, now we have, that's the little s, the N equals 1 s subshell, and this is the N equals 2 s subshell, okay, out here. But we have options now, because we're at N equals 2, we can actually have a P or an S, right? Now remember, in the Bohr model, what we're about to look at is not the Bohr model, but it's the reality of the situation. In the Bohr model, this is the N equals 2 S shell, so 2S. But the N equals 2 P shell actually looks like this. It kind of looks like a little dumbbell. So, and then you can also look at it a different. you can, they have different ones. So there's 2 electrons, and there's 2 electrons, and then there's 2 other electrons. So it's very weird, I know, but I just wanted you to have a sense of the fact that these things actually do have like this sort of hazy cloud of where electrons are at any given time. And it's super weird the way that it all works out, because like these represent where electrons sort of pop in and out of existence. So it's pretty weird. But here's the thing, that looks kind of like a donut, right? Or it looks kind of like a let me go back to this one because that makes more sense. It looks like a dumbbell, right? They actually call it dumbbell. But that's like, all that is just a graph of where the electrons sort of hover and buzz around like bees. I mentioned it like bees before. And so all they do is they take up space. They don't really take up space necessarily with where they are. They take up space with where they could be, if that makes sense. And so, anyway, we'll get out of here and get to something that makes that makes a little bit more sense. Back to the Bohr model of the atom. Essentially, this we say that this takes up a certain amount of space, and then when we get to the next shell, which is the n equals 2 shell, then we have to break it down into layers. So what I really should do here is say the red one is the S shell, and the blue one is the P shell.
What do S and P stand for?
Great question. So you may remember that in the spectroscopy part, I mentioned there were a bunch of spectroscopists that were like staring at graphs, right? They were like, hey, I noticed if I stare at a hydrogen gas and I make it glow, right? I just make it shine, you know, kind of actually a lot like your fluorescent lights in your ceiling. You know, there's like 1,000 volts across those, and it makes it glow, right? So they would just do this with pure gases like hydrogen, helium, neon, you know, argon, things like that. They would just take this with pure gases, and then they would get the opposite of what they had in that solar spectrum that I gave you. It had basically the spectrum of the core of the sun, and then it had gaps missing out of it. You remember the gaps in the video that I was talking about? Well, if you look at hydrogen, you get exactly the opposite of that. You get like a peak where one of those solar gaps is, and another peak, and then you get another peak. But the way that they would show up is it'd be like this. It'd be like very sharp, and then there's a big one here, and then there'd be one that's like this, right? They didn't know what this meant, so they were like, well, let's see, this is the biggest one here. It would be actually much bigger than that, like boom, you know, like that. And they'd say, well, that's definitely the principal peak, right? And then over here, though, this one was rather sharp, so they would name that one the sharp peak, that one the principal, and then this one was the diffuse peak, right?
Oh, okay.
You seeing where this is going?
Yeah.
And then there was another one called fundamental, and I can't remember what that one looks like, but for that reason they started naming them the S peak, the P peak, the D peak, and the F peak. And Bohr was the one that figured out what they were and why they were different. So these diffuse peaks happen from the D shell. They happen a lot with metals and transition metals, the ones that are in the middle of the periodic table, which we'll look at a little bit in chemistry. But I'm going to put a lot of chemistry videos. I'm going to start putting out videos this week for next week, connect all of this to chemistry. But anyway, I get that. It's fine. Just keep up the questions.
Okay, this has to do with like the Bohr model and stuff.
Correct.
I don't understand. Like, I don't understand where you get the numbers for the protons and electrons, what the boxes stand for. I don't get any of it. Like, I don't get it.
I'm sorry, guys. Somebody's walking outside again. Simon.
He's not bothering me.
Okay. Let's look at the periodic table, and I want to ask the questions like. I like this dynamic periodic table. I showed you a picture of it, but really you should go to the site. It's actually pretty amazing. Okay, so let's take a look at a let's go back here and let's build an atom, shall we? What did I just do? That was weird. Okay, let's build an atom. Our atom is going to be built from, here's our first n equals 1 shell, n equals 2 shell, n equals 3 shell. I could go further, n equals 4 shell, and you got the picture, right? Now tell me at what point you're like, whoa, stop, that's not making sense. Okay, what I want to do is I want to put together a nitrogen atom. Okay, so the first question that I have to do is I have to ask, what's the most important question for what is a hydrogen atom? Absolutely most important thing. What defines it as a nitrogen atom?
Number of protons.
Exactly, yes. Number of protons. So we check
Had that in the video.
our periodic table and say, okay, it's not resizing very well here. But if we check our periodic table, there's 1, 2, 3, 4, 5, 6, 7. It's the atomic number 7, right? That atomic number is also the number of protons. Not by coincidence, but because that's how we define it. So then we have the number of protons is equal to 7. Okay. Now we can put this in a notation by looking at we're going to look at the standard nitrogen here. Remember, there are different types of, you can have different amounts of neutrons in nitrogen. You just can't have different amounts of protons, right? So we're going to look at this that's on the chart here is given as it has a mass of 14, so its atomic mass is 14. So you can see there it said 14.007. That's actually just like an average of all the different masses of different types of nitrogen. For a standard nitrogen, it's just 14, and then you'd get what? How many neutrons does that mean?
Wouldn't it be 7?
That's correct, because we know that the total mass is 14, and then the number of protons is 7, so the rest of the mass must be taken up by neutrons. So this is the way we're sort of building our atom. So I know that I've got, and if you want, you can just like 4, 5, 6, 7, and then 1, 2, 3, 4, 5, 6, 7, right? Just put them like that. That's fine. Okay. So far, we're good.
Yeah, so far.
Okay. Now we're going to say that it's neutral. Okay. And if it's neutral, then that means that we have how many electrons?
0. Or 7.
One of those is correct. So if we have yeah. Huh?
I was just gonna say, doesn't it have to be like a -7?
That's the idea. See, what we have right now is currently has a charge of +7. The neutrons don't do anything for charge, right? So right now we have 7 positive charges by the protons. If we want to make it neutral, we need to have 7 negative charges. So that the +7 and the -7, they cancel each other and it's neutral overall. Does that make sense? Okay. Okay. If it doesn't, let me know, because we're about to start building it with our electrons. Okay. So now we place our electrons, and we say, okay, let's take our first electron. Where does it go? Whoops, that's not what I meant to do. Our first electron, where does it go?
Doesn't it have to go on n=1, like on the 1?
Correct. Yes. So our first one goes here somewhere. And then our next one.
And this is a neutron?
No, neutrons are way deep down in the nucleus. These just,
So they're in the middle.
all they do is just be heavy. They don't really do anything else.
Okay, so which one is this?
This is electrons, the tiny little things, the bees that buzz
But
around.
we have another one on the like on that first shelf again.
Yeah. So we had the first n=1, and then we're looking at the S subshell, which really that's only shell that exists on that n=1, right? And we have 2 electrons there. Good. We have 5 more electrons to go, right? So we've accounted for, let's see, 1, 2. Now we need to put some more in. So what's next?
To go to the second.
Right. And so we're gonna separate this into subshells now. So we're gonna put some of them on the, I don't want to use that. Some of them are gonna be on the S subshell, and some of them are gonna be on the P subshell. So we'll make the S subshell here is gonna be the black subshell. Oops. And the P subshell will be the purple subshell. Okay. Is that okay?
Why do we have subshells?
I don't mind you asking. I don't know what you mean by the. Why do they exist?
Like, yeah, I guess. I don't understand. Like, I'm lost. I don't understand what 1s squared means, and I don't understand the s and p.
Okay.
Serious, Shane, did you watch the videos that he posted?
Yes.
Oh, okay.
What the?
I was just wondering if he was explaining.
And they. Yeah. Okay. Well, I think that's a fair question. That's a. Okay. The. How to answer it though is the. We don't. This is one of those things that we're not actually saying, hey, let's just organize it in this way. This is actually one of those things that nature did and we noticed. So we don't necessarily have a lot of power over this. This is just what we noticed that atoms do.
Okay.
So we named them with letters, but other than that, we're just sort of
So
like,
p is just the name of the subcircle or sub.
right. And the P is in actuality, it's those dumbbells that we were looking at. But that's really hard to draw, so we just draw it as a circle
Okay.
on here. So okay. All right. So we want to put some more electrons in here. We still have 5 more to go, right? So let's get started on that. What's next? We definitely can't put any on the n=1. That's full, right?
So now we gotta go to the next level, S.
Yes. So, And you can also, if you want, you can say, okay, here's n equals 1, n equals 2, n equals 3, n equals 4, and we'll put a different representation on here, okay? Where we get, there's the S shell, sorry, that shouldn't be there, the S shell for just one layer, right? And there is a little pocket for 2 electrons to sit in. And then we get the n equals 2, we have the S shell, and then we have the P shell, which has 3 pockets for pairs of electrons in it. Why? Because that's what they do. We don't know why. This represents one dumbbell, this represents one dumbbell, and this represents one dumbbell. Okay? So, I know that's weird. But anyway, this is the P. So then we have more options, in other words. You could think of it like a movie theater, like you only have 2 seats here, and then you have 2 seats here, and then you have 6 seats here. And then when we get to the third level, I'm probably going to have to make some more room here. It also has an S, and it has a P, and a D. And each of these circles holds 2 electrons in it. Okay? So you can just build it up like this. 5. Would have an S, a P, poo, and a D, and an F. And it would just keep going. You just keep going and going and going and going. So you get more options as you go up in shells, right? Again, this is just something we notice happens, right? We have managed to fill this one, and sometimes what we like to do is put a little arrow, an up arrow and a down arrow, to show that we have successfully filled our 2 seats here. I'll use something a little bit more visible. It's okay if you want to do that. Okay, so there are 2 electrons. And then we need to keep filling these. So where do they go? Well, they go. The next one up is the n equals 2, the S shell, right? We need to fill those. So we get one here, one here. Good. We got to mark those off up here. There's 1, 2, 3, 4. And then we need that. We don't have any more in the S. Let's go ahead and mark this as 2. This is n equals 2, and we have another S shell, so this is the 1s and this is the 2s. And then we managed to put 2 electrons in there. We should note that up here. There are 2 electrons in there. Okay, so now this isn't squared. It's not a squared notation. It's just the S is carrying a little briefcase with it that says how many electrons you got in there. So, alright, and then we move up again, and we say, okay, how many more do we have left? We have 4, and we need 7, so we're going to do 3 more. So 1, 2, 3, right? 3 more electrons. Where do they go? It turns out that, and I didn't mention this, but it's okay. It doesn't really matter. It turns out that they have a tendency to do this. They don't like being squished together. So anyway, the point, if you did it a different way, that's fine, as long as all 3 of them are up here in the P shell, okay? And that means that I got 3 more electrons that need to go in this purple one here. One here, maybe here. It doesn't really matter where you put them on here. They just have to be on the P ring here, right? And that means that I now have 2P, and then in the 2P, this is the 2P level right here. In the 2P, I have 3 electrons, so that's the notation for it. Is it starting to make sense?
Yes.
Oh, good. Okay. Yeah, I know that the SPDF thing is weird. And the more you study it, the weirder it gets too. So, I don't know if that's good news or bad news to you guys, but like, I don't know. I guess just You have to get comfortable with weirdness. Okay, how many valence electrons does this thing have? We talked about valence electrons in the video as well. This diagram here is super useful for determining that stuff.
Okay. I don't remember that part.
Alright, so the S is filled.
Mm-hmm.
This S is filled. This one's not. Right? The P shell is not filled. So how many electrons does that have, the unfilled shell, have in it? It's 3, right?
Mm-hmm.
So it's a valence, 3 valence electrons. What's important about that is that these ones that are filled here are happy. If you get S and P shells that are filled, they are happy shells. S and P are the ones that you have to keep happy. They want to be filled so badly. It's like you know, if you have it's kind of like if you have a house and you've got like 6 rooms in the house for kids, and you're like, we have 5 kids, right? we we've got 6 nurseries or 6 bedrooms for kids, and we've got 5 kids. Like, where's the other kid? You know. And so like, and so if you want to put a kid in that room, you know, like I don't know if you do, but like but like it's the atom has a tendency to want those spots to be filled. It always knows that there are 6 spaces, and it always wants there to be electrons in them. And nitrogen's a little bit weird because it's just as far away from being filled as it is from being empty, right? So the P shell there, it would be happy with either. It'd be fine if there were no electrons in the P shell, or if there were all 6 of them in there, but otherwise it's just going to be unhappy until you do something about it. Okay. They love being filled. So for that reason, the S's here don't matter to other atoms that are wandering around in the vicinity. They don't help it like interact in any way. But the P shelled here in this nitrogen case, it does. Now, let's do another example so that we can be clear about what I mean by that, okay? Okay, let's do another example. Let's build, and I don't want you guys to try to build this one, okay? Let's build, I want to build a sodium atom. And a sodium you can see over here, you might not recognize it by its chemical symbol immediately because it's got that weird dumb Latin thing, Na, but the word is here, sodium, so Na, okay? So we're going to do sodium atom. Na. Sodium, okay? Now, what's the first thing we figure out?
How many protons?
Yes. And how many does it have? Is it hard to see on there?
Yeah, I'm having trouble seeing.
Sorry.
No, you're fine.
Is it getting? It's not getting bigger. Maybe I can. There we go. That's a little better. Okay, can you see it now? It's a little better.
Yes, I can see it.
What do we got?
Thank you. I'll put my glasses on.
Anybody can.
11.
Yeah. The atomic number is 11, and therefore we have 11 protons. Good. What's the mass of this thing about? Not exactly, but about.
22.99.
Yes. So like if you had to turn that into an integer, it would be what?
23.
Right. meaning that most of the atoms, most of the sodium atoms have a mass number of 23. Okay. There's a few of them that are lighter than that, which is why it averages out to a little less than 23. Okay. Okay, so that means then that we have the number of neutrons is
So it would be 12.
yes, it has 12 neutrons and 11 protons. A lot of the times the amount of neutrons in these lighter elements is about the same as the amount of protons. It tends to stay that way. See, as you can see for magnesium here, it's got about 24, a mass of 24, and 12 of them are protons and 12 of them are neutrons. So we would actually write this as 23 sodium, and then there's a 12 there. Is actually it's kind of dumb to put the 12 there. It's not even necessary because it's like the sodium tells you that that's 12 protons. So there's putting the 12 here is, I don't know, if you like that, that's fine. If you, it's really it's just repetitive, really. Okay, so let's build our atom, and this time, you know what we're not going to do is we're not going to put a big atom there. Instead, we're just going to say, hey, let's put our n equals 1 shell, our n equals 2 shell, our n equals 3 shell. Put a little bit more space in here. Okay, n equals 4. And we have, a lot of times I use boxes. I used circles earlier because it was easier, but we can use boxes, it's fine. N equals 1 has its own S shell. N equals 2 has its own S shell, but it also has a P shell, right? Or subshell, excuse me. That's a mistake I make a lot. I say shell when I mean subshell. N equals 3 shell has an S subshell, a P subshell, and a D subshell. We're not going to use all these, but you know, it doesn't hurt to get used to using them. And then each of these has our electrons in it. So let's go with how many electrons do we need to make for a neutral sodium atom? We kind of presume when we use the word atom, we presume they're neutral unless someone says ion. So if it's ionized, then that means that we messed it all this counting up on the electrons. But if it's not, then it's just a regular atom, then we can always count on it to have how many?
11.
Yes, exactly the opposite of the protons, or the same amount as the protons, so exactly the opposite charge of the protons. Okay, so neutral atoms, in other words, to make sure everybody's totally clear about that, neutral atoms always have the same number of protons and electrons.
Okay.
Ions do not. And all I have to do to make this an ion is come in and like bully one of these electrons to kick it off. Okay. Turns out not to be that hard on this particular atom. Okay, so, and we'll see why. Actually, you'll be able to see why. So let's go ahead and start this process. We have 2 that go in here, right? And then we have 2 that go in here. There's another 2 right there. And then we have, how many can go in here?
3.
Each one can have 2.
Right. Each one can have 2, so 6.
6, yeah. You got it. So 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6, and that gives us 10. We have one more, so it goes up here.
Right.
Okay. All right. Now, first of all, I want to make sure everybody's clear with the process of filling these up from the bottom up, right? Okay. Then how would we write this out in our electron configuration notation? We always start with 1s. How do we write it?
1s, and it would be 2.
Next.
And then it would be 2s2. Then it would be, let's see, that would be the p, so it would be 2p6.
Correct.
And then 3s1.
Exactly.
Yeah.
Exactly. Now remember, these S and P shells are all very important. When you get to D shells, they're kind of pushovers, but when you have S and P shells, they're very important. They want to be very filled or very empty, right? So you can see that this sodium atom here has an entirely filled n equals 1 and n equals 2 shells. And then it's got this one electron that's just sort of wandering around on that third level. It's not very welcome. So this would be more like you have 6 kids, well, 8 really, 8 kids down here, 6 of them on one side of the house and 2 of them on the other, all in rooms, and then you have one extra kid you don't have a room for. So that kid has to stay in the doghouse. Okay? That's that's the way this atom behaves. And so if some other atom comes along and says, hey, you've got an electron, can I have it? You're like, yeah, we didn't like that kid anyway. Does that make sense? Does that make sense? Okay. And then you'd have
The husband would be happy if the kid in the doghouse, but not the husband.
yeah. So this is okay. This is generally how this goes for like how why this electron out here is very important. It means that this this atom has how many valence electrons?
It has 1.
Yes, 1 valence electron. The valency of the atoms determines their chemistry. It determines how they interact with other atoms. Okay, did this process make sense? Okay, so you don't really even need the circles. I kind of used that as a visual, and the reason that I did that is because when I was introduced to this, they just gave me all these boxes, and I was like, what the hell am I looking at? There's just a bunch of boxes, right? So hopefully you have a sense of what's actually happening in the atom, and then also this presents an easier way to stack up the electrons and know how they, not, in other words, be able to build the electron configuration without problem. So, is that making sense, everybody? Does anybody have any questions about this so far?
I'm good. I don't know about everybody else.
I'm good.
This is basically okay. So there's only one other thing that went through, and that was the video on energy. And I know we don't have a lot of time today, but don't forget that that is all the videos for this week. At least, technically for this week. I'm going to get started early on next week's videos because chemistry is hard. But at least it is for me. This stuff is easy for me. Chemistry, remembering names is super hard for me. So, but anyway, it might be easier for you guys. I don't know. But anyway, so anyway, this plus the energy of the atom is the absolutely the end of atomic physics, if that makes sense. So now let's did I oh my gosh, oh no, okay, I thought I kept recording my video for 2 hours, but I didn't. Alright, I'm gonna move to another layer here, so that way I'm preserving these layers in case anybody has questions about them. We can go back. Now electron volts. How are you guys doing with electron volts? That was the fourth video.
Oh, I didn't get all the way through that one yet.
I see. I want you to know that the way that okay, so let's do this real quick. You know how to do a unit conversion for, I am, my height is 5'7" when I'm in a really good mood and I just woke up in the morning. Okay. Otherwise I'm shorter than that. So if we take 5'7" and we wanted to convert that into centimeters, then how would we do that? First of all, let's make this inches. That would make it better, right?
Put in inches.
Yeah,
So
that would be 67.
60, so it would be 67 inches.
Good. Okay. Now, how many is that in centimeters?
I don't know that far. 67
Okay.
inches is how many centimeters?
Well, the first thing we
How
need,
many centimeters are in an inch?
right? That's the first thing you need is the conversion factor, right?
Right.
Okay, so 1 inch is equal to 2.54 centimeters.
That's right. You told us that.
Oh, no, you don't have to remember it. I'm just saying that what you have to do is remember that you need the conversion factor. That should be the first thing you go for. And now we have the conversion factor, and we put which one's on top, which one's on bottom.
Isn't the 1 inch down bottom?
That's correct, so that it can cancel this one over here, right?
Right. So it's 2.54 on top and then 1 inch on bottom.
Good. Oops. Okay. And so then we can always go to our calculator over here and just say I am 67 inches times 2.54 centimeters per inch, or 170. I am 170.
Do we not include the .18? Is that irrelevant? Because is it insignificant? You know.
Yeah, it's okay if you include it, it's fine. The way that I set up my quizzes is that it takes the answer. If you were to get like 165.5 or 170.5, it would still count it right.
Okay.
So that's not important, but if you put it in, it won't hurt you.
Okay.
Okay. Now let's try this again, but this time we're going to say that something has a certain number of joules of energy. Okay. Let's say that I have something that is millijoules. What would millijoules be? I'm going to say it has 0.4 millijoules of energy. What is a millijoule? Just based on what you know about the word milli, or the prefix
Doesn't
milli.
that mean 1,000?
It means 1/1000th. Yeah.
Okay.
Like a millimeter is 1/1000th of a meter. So this is going to be 1/1000th of a joule. So I need to move my decimal place over even more
Right.
than it was before, right? Or you can say it is equal to, now that would be 4 times 10 to the negative 4, because my decimal moved to the left. So times 10 to the negative 4.
Equation.
Yes, joules. So now we have it in terms of joules instead of millijoules. Okay. Now what if I wanted to turn that into electron volts? I need my conversion factor, the same as I did with my inches and centimeters. The conversion factor is that 1 electron volt is equal to 1.6 times 10 to the negative 9. What the heck is that? Times 10 to the negative 19 joules. That is the conversion factor. So we would do the same thing, right? And I go to the next line because we don't have as much room. We have 4.00 times 10 to the negative 4 joules, and we need our conversion factor here. And which one goes on top, which one goes on bottom?
The 1.6
Right. Because joules is over here. We need that to cancel. Right?
Mm-hmm.
And then the 1 electron volt is on top. That allows us to get this in terms of electron volts. So we'll go through over here and do the same thing. Okay, we have 4 times 10 to the negative, and remember, y'all can do times 10 to the power of negative 4, or you can do it as 4e negative 4, whichever you like, right? And that needs to be divided then. Let's go back and look at what we're doing over here. We needed to divide that by 1.6 times 10 to the negative 19, since that's in the denominator, right?
Right.
Okay. It's 10 to the negative 19. Okay, and that's what we get. Okay, we divided by a very small number, and we ended up with a very large number. This is a super large number. It's not just a large number, it's a very, very large number. But that makes sense because units of electron volts are very tiny. So it's kind of ridiculous to talk about some big object like a fist or a or a soccer ball as in terms of electron volts. We usually reserve them for things like light and atoms. But this one is going to be 2.5 times 10 to the positive 15 electron volts. That is a heck of a lot of electron volts, right?
Mm-hmm.
That's all it is. It's just a unit of energy, but it's a little bit more convenient because in atoms the number of electron volts is something closer to like 1 or 2. So that it helps us to kind of get a sense of, it's much easier thinking in terms of 2 electron volts rather than 3.2 times 10 to the negative 19 joules. Nobody cares about that crap. So it's so much easier to talk about it in terms of electron volts. Does that make sense?
Yes.
Okay.
To me it does, yes.
And if we wanted to talk about the sizes of the atoms, then we would talk about them in terms of nanometers instead of talking about them in terms of meters, right? So it's the same. It's the same idea, just a unit conversion. So I don't want everybody to. I gave you why we call it an electron volt in the video. I described why, but you don't have to really know that. I just like to give a little bit of background information on this stuff. But this is, this is the unit conversion. If you got that down, then you can get electron volts with no problem.
Okay.
Okay. The only other thing that we have is like calculating energy levels, like how much energy is in a certain energy level and what is the difference between one energy level and another. Which is what Bohr did. And we can keep doing that on Thursday or tomorrow. If anybody wants to meet tomorrow, that's fine. I'm here for you. If I don't hear from you, I'm just not gonna show up. But if y'all have, I certainly don't mind. Not at all. It's no big deal for me. So.
Okay. That's cool. Well, I'll finish watching the fourth video, and then if I have any problems, I'll email you.
Yeah, y'all can always email me too. And again, sometimes if you email me, I'll just email the whole class if it's really a good question.
Okay.
Okay. Anybody have any other questions or anything?
Not yet. Not be getting some emails later.
That's what I was thinking.
It's totally fine. It's totally fine. That's what I'm here for. I wish I could say I was there for you, but I'm not. I'm here for you. So that's just how it goes. So, do y'all know anybody in the class that's power outed?
I don't have everybody's number, so I can't answer that.
Okay. I
No, I don't.
just want to check in on people. I noticed.
That was Molly.
I noticed Stormy didn't show up today, so I wasn't sure if that was because she's just like I don't have to, so I'm not gonna, or if it's.
But no, I haven't heard from her either.
Yeah, she may
Maybe
just.
she doesn't have any power.
Yeah, her cell phone might be dead now. That's frustrating.
Yeah.
It all should like run by and throw batteries at her or something through her window. It's just trying to be nice. So,
Right.
um, okay. Well, okay. Again, let me know if you want to meet tomorrow, and let me double check to see if anybody's been sending me messages on here. No. Okay. Um, all right. I'll go ahead and close out this meeting. Please let me know if you've got more questions. Okay, guys.
Okay.
Okay.
Thank you.
All right. Y'all take
Have a
care.
good day. Bye, guys.